this video, we're going to introduce the first of our derivative rules. So in the last video, we defined the derivative as the limit of the difference quotient as h approaches 0, specifically where we think of h as the distance between two x values associated with 2 points on the graph of a function. So if we allow the distance between those two x values to approach 0, which also means the points are approaching one another, then essentially we take the slope of a secant line that passes through 2 points on our graph, and we can use that secant line to approximate the slope of a tangent line to a single point on that function's graph. So the geometric application of the derivative is that the derivative represents the slope of the tangent line at any particular location on a function's graph. So in talking about a derivative rule, essentially the derivative rules are going to give us other options for how we can evaluate a derivative. So we evaluated the derivative using the difference quotient, but we used typically fairly simple functions to apply the difference quotient to. So you can probably imagine that as the functions become more and more complex, simplifying the difference quotient would also become more and more complex of an activity to do. So particularly if we're looking at something with higher exponents, or maybe looking at something that has both exponents and then some other type of algebraic operation, maybe a square root, maybe a logarithm, something like that, evaluating the difference quotient, simplifying it to the degree that we can just plug in a 0 in place of h and take that limit, that becomes increasingly complex to do. So fortunately, we have other options for evaluating a derivative, and they come via what we call these derivative rules. So derivative rules are going to allow us to simplify derivatives depending on what kinds of algebraic operations we see within the function we're differentiating. So before we introduce our rules, let's talk a little bit about notation. So when we introduced the derivative in the last video, our notation for the derivative was prime notation. So the derivative of the function f of x is f prime of x. So the prime is there indicated that we're taking the function with the same name, so the function f, but the prime indicates that this new function is the derivative of the original function. So this prime notation is actually called Lagrange notation. It's very similar to Newton notation, which is named for Sir Isaac Newton. So calculus is kind of interesting. Calculus was actually developed by two different mathematicians in different parts of Europe at the same time, although they were not working together. So they also had competing notations for representing this, this concept of the derivative. So this particular notation is one we use frequently. We also have another notation called Leibniz notation. Leibniz was one of the competing mathematicians that developed calculus other than Sir Isaac Newton. So rather than writing f prime of x, if we treat y as a function of x, in other words, if we think of y as being equivalent, equal to f of x, then another notation representing the derivative is this notation. We can also write dy over dx. The way we would read this is the derivative of y with respect to x. So we're thinking of y as our output, we're thinking of x as our input, and we're taking the derivative, treating x as the input variable. So this is another notation that can be used to represent the derivative. Based on combining these two notations, using these notations in different ways, there are a variety of ways to write the same thing just using different notations. So all of the following would be considered equivalent notations, telling you to do the same thing, telling you you're looking for the same thing. So our prime notation, f prime of x, could also be written, as we've just seen, dy dx. Again, we read that as the derivative of y with respect to x. Another way of writing the Leibniz notation using something similar to the Leibniz notation is going to be this. If we write d over dx, and then inside we write f of x. That is also going to be an equivalent notation. So this notation, you can think of this as being more of a verbal form of this. We think of dy dx, the derivative with respect to x, think of that like a noun. That is the derivative. That's the thing we're looking for. D dx is more like a verb. That's the indicator that we want to take a derivative. So this, kind of like seeing a plus sign tells us to add two things together, this particular notation tells us take the derivative. It's like the verb saying to take the derivative. Well, this is the derivative with respect to x of the function f of x. So these two notations are very similar, again, because we're thinking of y as a function of x. So y and f of x are essentially interchangeable. And then another, probably the most simple way to use our notation, rather than writing f prime of x, since we think of f of x and y as being the same thing, another really simple notation is also y prime. The benefit of this notation versus this, though, is notice in this case we don't actually see any of the additional variables involved other than the variable y. So here, f prime of x, we can specifically see what the input variable is, the variable that we're differentiating with respect to. Now also, when we specifically want to evaluate the derivative, in other words, find its actual value at a particular value of x, or whatever we're thinking of as our input variable, the variable that we're differentiating with respect to, we can also write these notations. So f prime of some number, which we saw in the last video, this is telling us find the derivative for our function f, and then evaluate that expression at an x value of c. We're going to think of c as a constant. And then if we want to write something similar using the Leibniz notation, this would be an equivalent way to say that we want to evaluate our derivative at a particular value. So again, this represents the derivative. In this case, this would just be a formula for the derivative. But if we draw a vertical line, and then at the very bottom of the vertical line, we write x is equal to some constant, this notation also tells us find the derivative and then evaluate the derivative using an x value of c, whatever that constant c happens to be. So all of these notations are used pretty much interchangeably. In certain situations, the prime notation will be easier to use just because it's going to be less writing. But in certain situations, just because we need to be a little bit clearer about what exactly is happening as we take the derivative, using one of the Leibniz notations is going to be more beneficial. So just keep in mind, all of these notations are essentially interchangeable. We use different ones in different situations, just depending on what kind of function we're looking at, what kind of derivative we have to take. So now let's talk about some of our derivative rules. So we'll start with the most basic rule. So suppose we have a function that is a constant function. In other words, something of the form f of x is equal to c, where c is a constant. So the thing to pay attention to here is we're thinking of x as our input variable, but notice that the function rule for the function f does not involve the variable x. It's just a constant. We don't actually have an x there. So based on the fact that this is the function we want to differentiate, where c is just an arbitrary constant, not a specific constant, we want to find the derivative with respect to x of this function, which just has a rule that's a constant rule. So remember, this is like the verb saying take the derivative. It's telling you to take the derivative, and inside parentheses is the function, in this case the function rule, that we want to differentiate. So we can actually find this derivative using the difference quotient. This one is fairly straightforward. So let's recall what the difference quotient is. Remember, the difference quotient is defined as f of x plus h minus f of x all divided by h. And if we then take the limit of this expression as h approaches 0, that by definition is the derivative. Okay, so if we're going to simplify the difference quotient for this particular function, remember we go term by term. So f of x plus h, that's telling us to take the rule for f and substitute in a specific input of x plus h wherever we see the generic input x. But again, notice based on this function rule, there is nowhere to substitute in a value of x. So regardless of where we're evaluating this function at, the function is always identically equal to c, whatever this constant is. So f of x plus h is actually just going to be the constant c, because again, there's nowhere to substitute in x plus h. There is no specific location for the input in that function rule. Now in the same way, f of x, we're subtracting f of x. Well, f of x is also just c. So our numerator is just going to be c minus c, and then of course we have our h in the denominator. Well, anything minus itself is going to be 0, so that's going to be 0 divided by h, which just simplifies to 0. And so if we then want to take the limit of our simplified difference quotient, so we're going to evaluate the limit as h approaches 0 of our simplified difference quotient. What is that going to be? Well, again, notice we typically want to evaluate algebraically. That's what we did when we evaluated these difference quotients, took the limit of those. There's nowhere to plug in h equals 0. So the limit of this constant is just going to be the constant. In this case, there's nowhere to evaluate with h equals 0, so we can't do anything else. So in this case, this is going to be the derivative with respect to x of our function f of x, which again was just a constant function where c is our constant. So the derivative is identically 0 anytime our function is a constant function. Now graphically, let's interpret this graphically, and we'll see that this actually does make sense. Intuitively, it does make sense. So let's graph the actual function f of x is equal to c. Now keep in mind, we don't know what c is. It's an arbitrary constant, so we're just going to graph with respect to some arbitrary value. Now don't forget f of x means the same thing as y. So f of x is equal to c is really the same thing as y is equal to c. Well, the equation y equals c represents a line, but specifically it represents a horizontal line. So if you were to imagine drawing a horizontal line, let me scoot it down a little bit. Imagine drawing a horizontal line, specifically passing through the value c. So c is going to be some arbitrary value, we don't know what it is. Keep in mind, it doesn't necessarily have to be a positive number. It could be below the x-axis. Here, it doesn't really matter. But if you remember geometrically what the derivative represents, it represents the tangent line to the function's graph at any particular single point. So let's pick a point, doesn't matter what it is. Imagine drawing a tangent line. In other words, a line that just touches that particular point on that graph, but doesn't necessarily intersect other points. Well, the only way we could draw a line that's tangent to the graph, in other words, lays against the graph, is parallel to the graph, but also passes through that point, would be to draw a line that actually coincides with the graph of the function itself. Well, what do we see about that tangent line? Well, that tangent line is also a horizontal line. And we know that the derivative represents the slope of that tangent line. Well, if the tangent line is a horizontal line, every horizontal line has a slope of 0. So in this case, the derivative is 0, because based on what our function's graph looks like, every tangent line to that graph would also be a horizontal line. Every horizontal line has a slope of 0. So for any constant function, notice we did this just for an arbitrary constant. It's not a specific number, it's just an arbitrary constant. This is true in general for any value of c. Based on that, we can officially say that the derivative of a constant function is always going to be identically equal to 0. So that leads us to what we call the constant rule. In other words, the derivative rule for a constant function, where we don't actually have our input variable, we just have a constant. So the derivative of a constant function is 0, regardless of what the function is. So another way of saying that, to write that more officially, that is the derivative with respect to x of a constant function, where c is considered to be a constant, is going to be 0 always. So anytime we have a function that is just represented by a constant, not an actual variable, but a constant, then the derivative of that function is going to be 0. Okay, so let's build from there. Let's look at slightly more complicated situations. Let's look at another rule. So this next rule is going to be one of the most versatile rules we have as we take derivatives. We call this the power rule. So if the constant rule is going to allow us to deal with functions that have just a constant, the power rule is going to allow us to deal with functions that have a power or an exponent. So the power rule allows us to take the derivative of functions that contain a variable raised to a power, otherwise known as an exponent. So here's our power rule. For any real number k, we're going to think of k as our exponent. If our function is defined as y is equal to x to the k power, so again, k will be a constant just like c was a constant. Y and x are our dependent and independent variables. Here's the rule. If we want to take the derivative with respect to the variable x, treating x as our input, of this function, x to the k power, then here is the rule. The derivative is defined as k, the constant k, times x raised to the power of k minus 1. That is going to be the formula for our derivative. Anytime we take the derivative of a function that looks like this, our variable raised to a power, regardless of what the power is, as long as the power is a constant number, this is going to be the formula that allows us to differentiate that function. So here's how I like to think of it. What's really happening in this formula to go from the original function to its derivative? Well, what you can think of it as taking the power, think of it as bring the power down, bring it out front, it becomes a factor, it becomes a coefficient, something multiplied by x. So we bring the power down, which results in the k out front, and then we decrease the power by 1. In other words, we take the original exponent and we subtract 1 from it. So bring down the exponent and then decrease the exponent by 1, and that will give you the derivative of that particular function. So this is actually a very versatile rule. It's going to allow us to deal with a lot more situations than are readily apparent. There are situations where we don't explicitly have an exponent written, but we can rewrite expressions involving exponents, and then we can use this power rule here to differentiate our function. So let's try a few examples. So our first function is defined as y is equal to x to the 5th power, and we want to take the derivative of this function. So in this case, the derivative of y with respect to x can be determined by the power rule, since we have our variable raised to a constant power. So the power rule says bring down your exponent, so bring down the 5, it becomes the coefficient, it becomes a factor, and then multiply by the power, the base to a variable, or a base to an exponent, excuse me. But the new exponent is going to take the old one and subtract 1 from it. So if we simplify all of that down, that's going to be 5 times x to the 4th power. That will be the value of our derivative. Now let's try another one. Y is equal to x. Why does the power rule apply here? Well, we've got our variable. Even though the exponent is not written, there is an implied exponent. Anytime we have the variable without an exponent written, remember there's an understood exponent of 1 there. So what would the derivative of y with respect to x be for this function? Well, same rule. We're going to take the exponent, bring it down, it's going to become a factor, and then we're going to multiply by our variable with an exponent, but the exponent is going to take the original exponent and decrease it by 1, subtract 1 from it. So if we simplify this, we have 1 times x to the 0 power. Now if you remember, x to the 0 power, or anything to the 0 power, anything to the 0 power is going to be equal to 1. So 1 times 1 is just going to be 1. So in this case, the derivative of y with respect to x for this particular function is going to be 1. Now, these are situations where we have a whole number exponent. What if we have an exponent that's not a whole number? Well, as it turns out, it doesn't matter. The rule applies in the same way. So the derivative of y with respect to x for this function, now we also have a variable raised to a constant power, same directions as before. We're going to bring down the exponent and then multiply by our base raised to the original exponent minus 1. So that's going to be 0.7 times x to the 0.7 minus 1. If you need to do that in the calculator, do it in the calculator. That's okay. So 0.7 minus 1 is going to be negative 0.3. Now, in the previous situations, we either ended up with a power that was a positive number or potentially 0. In this case, we went to 0. But notice here, when we subtracted 1 from the original exponent, the new exponent is going to be a negative number. Negative exponents mean something very specific, so I'm going to write a note out here to the side. If we see something raised to a negative power, we'll call it negative n, what that means is the same thing as division. A negative exponent tells us to take the reciprocal. So x to the negative n is the same thing as 1 over x to the n, to the positive version of that exponent. So a negative exponent does not make anything negative. It tells you to take the reciprocal and then make the base, or excuse me, make the exponent positive. So in this case, x to the negative 0.3, that negative tells us that we can take the reciprocal. And in general, we don't like to leave negative exponents when we can avoid them. So getting rid of those negative exponents, interpreting what they mean in terms of reciprocal, we're always going to do that. So 1 over x to the positive 0.3. And then because we can combine these together, write them as one particular term, 0.7 can also be multiplied by 1. Think of this as 0.7 over 1. We multiply our fractions straight across. So 0.7 is going to be our numerator, and our denominator is going to be x to the 0.3 power. So that would be our derivative in this case. Now what if we start with a negative exponent? Again, same idea. The rule applies in the same way. The rule is based on the structure of the function, not the specific numbers that we're seeing. So we have a base, a variable base, raised to a constant power. We bring down the exponent, so that's going to be negative 4. And then we multiply by our base, raised to the power of the original exponent, minus 1. So that's going to be negative 4 times x to the negative 5. Well, we know x to the negative 5, that negative exponent, remember that tells us to take the reciprocal. So that's going to be negative 4 times 1 over x to the 5th. Treat this as negative 4 over 1 if you need, and then we multiply straight across. So that's going to become negative 4 over x to the 5th. Now sometimes we may have a negative exponent disguised. So notice in this case we have y is equal to 1 over x squared. Originally this doesn't look like the power rule applies. Our rules are very specific in terms of the structure of the function that we have to have in order to apply that rule. So we have to have our variable base raised to a constant power. Well, we have a variable base raised to a constant power, but we have 1 over all of that. So looking at this originally, it doesn't necessarily look like the power rule would apply. But if we were to use this particular rule, this definition of a negative exponent, use it backwards. In other words, take something of this form, or of the form that we have right here, and convert it to a negative exponent, well, then we'll have something that looks like this, and we'll have a function for which we can use the power rule. So 1 over x squared could also be written as x to the negative 2, again, if we were to use this conversion backwards. And once we have it in this form, we can take the derivative. So the derivative of y with respect to x is defined as, bring your exponent down, so negative 2, and then take the original base, take the original exponent, subtract 1 from it. So that's going to be -2 times x to the -3. Take the reciprocal. Let's see if we can get to the final step in one step here. So -2 and then 1 over x cubed. So the -2 will be in the numerator and then the x cubed will be in the denominator. Now, one final special case. This looks completely unrealistic in terms of the power rule. We have a radical. A radical and a power are not the same thing, right? Well, not quite. There is actually a rule that allows us to take something in radical form and convert it to an exponential form. So the rule here, imagine we have, let's say we have a power of, I don't know, maybe we'll call it n, and then maybe we have a root that we'll call k. So we have something of this form. So we have our variable base, potentially raised to an exponent, but everything is inside a radical. Another way to write this is with a fractional rational exponent. So we have our base x. The exponent, if x happens to have an exponent, that's going to become the numerator of our fractional exponent. And then whatever the index is for our radical, the index, you can think of that as the number in the window. So here the number in the window is 3. If you see no number, it's implied that it's a 2 because it's a square root. So that is going to become the denominator of our exponent. So another way of writing this expression using a rational exponent would be x to the n divided by k power. So this would be the most general way to convert a radical to a rational exponent. Suppose you just have something like this though. Suppose it's just like this, which is what we have here. Well, it's implied that x has an exponent of 1 if 1 is not written. So that means if we want to convert it to a fractional exponent, that exponent of 1 will be the numerator of our exponent, and then the k, the index for the radical, will be the denominator. So another way to write this would be x to the 1 over k power. And keep in mind, just as we can use this particular rule in both ways, we can use these rules in both ways as well. Typically, fractional exponents are not considered a final answer form if they can be converted back to something that's non-fractional exponential cleanly. If converting back would make the expression more complicated than it already is, then we may leave it. Otherwise, we will potentially want to convert it back to a radical. It's really just going to depend on the situation. So in this case, we have y is equal to the cube root of x. So I can use the power rule if I take this radical expression and convert it to something with a fractional exponent. So the cube root of x could also be written as x to the 1/3 power. And then I have something that fits the power rule. So the derivative of y with respect to x, in this case, we're going to bring down the exponent, make it a factor, times x to the 1/3 minus 1 power. Okay, so here the biggest thing is going to be simplifying that exponent. So I'm going to go down here, 1/3 minus 1, we need to simplify that down. Well, we have a fraction minus a whole number. You can think of that whole number as having a denominator of 1. We know the rule for adding and subtracting fractions requires that we have a matching denominator, and in this case we don't. So 1 over 1, we're going to need to multiply by 3 over 3 so that we have that matching denominator of 3. So that's going to be 1/3 minus 3 over 3, which is going to give us negative 2 over 3. So that's going to be our exponent. So we have 1/3 times x to the negative 2/3. Now, negative 2/3, the negative means something, the 2/3 means something. So let's deal with the negative first. Now remember, the negative exponent means we're going to take the reciprocal. But be careful here, because notice our coefficient already has both a numerator and a denominator. So when we take the reciprocal and combine with that coefficient, we have a 1 in the numerator, but we have a pre-existing 3 in the denominator. So when we convert this using that reciprocal formula, that's going to be x to the 2/3 power in the denominator. So 1/3 times x to the 2/3. Now the 2/3 power technically could be converted back to a radical using this rule, but typically when we have a fractional exponent that doesn't have a numerator of 1, in other words, something that wouldn't just cleanly convert back to just a radical with no exponent, that's typically when we're going to leave the rational exponent in the form it's in and not convert it back to radical form. So again, it's honestly just going to depend on the situation. Sometimes converting back to a radical might allow us to simplify something else in the derivative expression, but in this case, there's nothing else we're going to be able to simplify. This is a fairly simple derivative overall, so we can just leave it with that fractional form. So again, the power rule is going to be one of the most versatile rules that we have. We're going to use it a lot, and we're going to use it in a lot of different forms. So another rule that we have, if we build on, for instance, the power rule, is going to allow us to differentiate a function that has a constant times some other algebraic expression. So the derivative of a constant times a function, or again, just think of it as just another algebraic expression, is going to be the constant times the derivative of the actual function. In other words, the algebraic expression that that constant is multiplied by. So the way we would officially write this is the derivative with respect to x of a constant times a function. In other words, something like this, a constant times a function that we'll call f of x is the same thing as the constant times the derivative of the function. So this is the same thing as the constant times the derivative of the function. So what actually happened here? Well, essentially what happened is the c got pulled out front. This constant that we're multiplying by this function, by whatever its algebraic rule happens to be, it got pulled out front. So essentially what this means is that we can factor out the constant coefficient before we take the derivative of the actual expression that it's multiplied by. So let's combine this with what we now know about the power rule and step it up and look at slightly more complicated functions than the ones we saw before. So again, same rules. We want to differentiate each of these functions using the rules we now have. So we have the constant rule, we have the power rule, and now we can differentiate the situations where we have a constant times another function. So our first function is y is equal to 7 times x to the 4th power. So the derivative of y with respect to x, let's write it in this really formal notation. So that's going to be the derivative with respect to x of our function, 7 times x to the 4th power. Okay, but the constant times a function rule tells us if we have this constant coefficient that's multiplied by this additional algebraic expression, then we can factor that out, and essentially it becomes independent of the rest of that derivative. And so we're left with the derivative with respect to x of x to the 4th power. So essentially at this point, the 7 doesn't matter for the purposes of differentiating. Now here what we're left with, the power rule applies to this particular function. So remember the power rule, what we just looked at, says that you can pull down the exponent and then decrease the exponent by 1. Now we still have that 7 out front, so it's going to be 7 times the derivative of this function. So let's see if we can figure out this derivative without writing out all those extra steps. We pull down the exponent, bring it out front, it becomes a constant coefficient, and then we multiply by our base raised to the original power minus 1, which would be 3. Now the only additional thing we can do now, because these are now 3 individual factors being multiplied, is we can multiply those two constants together, and that's going to give us our actual coefficient. So that's going to be 28 times x cubed. That's going to be our derivative. Okay, let's try another one. The next function, y is equal to negative 9x. So the derivative of y with respect to x is going to be the derivative with respect to x of our function, negative 9 times x. The constant times a function rule tells us that constant coefficient can be pulled out front. So that's going to be negative 9 times the derivative with respect to x of the expression that contains our variable, which in this case is just going to be x. Now remember, we differentiated a function that looks like this. The power rule applies here because there's an understood exponent of 1. So when we take the derivative of this expression, we bring down the exponent, that's going to become a coefficient, and then we decrease the exponent by 1, so that 1 will become a 0. So we have negative 9 times, bring down the 1, well we don't really need to write that, that's just a multiplied 1, it's just understood that it's there. So negative 9 times x to the 0 power. Well, x to the 0 power, that's just going to be 1. So negative 9 times 1 is going to be negative 9. Notice what happened here if we compare the original function to its derivative. Essentially, the x went away. So anytime we start with a function where it's x to the power 1 and then take its derivative like this, essentially that's just going to be eliminated. That factor will be eliminated, and then any coefficient we have, it could just be a coefficient of 1, but any coefficient we have, that's going to be the value of the derivative. Okay, let's try one more. So y is equal to 1 over 5 times x squared. Now we can interpret this a couple different ways, but first thing I want to do is I want to kind of break this into pieces. So anything that's constant can be thought of as a coefficient, even if there's division involved. So 1 divided by 5x squared, well, that 1 over 5, we could also think of that as just a 1/5 by itself. And then we'd just be left with that x squared in the denominator. Now, we don't currently have a rule that allows us to deal with division. But remember, anytime there's something in the denominator that has an exponent, another way to write that is with a negative exponent. So having that x squared in the denominator, another way to write that would be x with an exponent of negative 2. So this would be an equivalent way to write this particular algebraic expression. And by writing it this way, now we have a constant multiplied by a function, so we have a rule for that. And then the function, the algebraic expression itself, the power rule would apply to that. So the derivative of y with respect to x is going to be the derivative with respect to x of our function. And let's write this alternate form, since we know this is the form we can use our rules on. Rather than actually factoring out the coefficient, let's just think about what happens without manually pulling it out. So this is going to be the portion of the function that we're actually differentiating. Remember, we're going to bring down the exponent, it becomes a factor, and then we decrease the exponent by 1, but we have that pre-existing 1/5. So it just ends up being multiplied by whatever we get when we differentiate that expression involving x. So we end up with a negative 2 times x to the negative 2 minus 1, which is negative 3 power. So we have a few different things to combine together at this point. So the two constants multiplied together, remember negative 2, think of that as negative 2 over 1. The numerators multiply, the denominators multiply. So that's going to be negative 2 over 5 times x to the negative 3. Okay, but remember, negative exponents in general, we're not going to keep those because we have a better way to write those. So the negative exponent tells me, flip it, take it to the denominator. So my final simplified expression will be negative 2 over 5 times x cubed. And that's going to be my derivative. Now let's look at our final rules, at least our final rules for this video. And of course, we will continue to add on. As our functions become more complex, we need rules to be able to handle those more complex situations. So what happens when we have a function that involves addition or subtraction that involves a sum or a difference. As of right now, we've only looked at functions that have a single term. But what happens if we have a function that has more than one term? Well, we use what we call the sum rule and the difference rule. So the derivative of a sum or difference is going to be the sum or difference of the derivatives. So let's translate that into notation. So the derivative of a sum or difference, and it's implied a sum or difference of functions. So the derivative with respect to x of a sum or difference of functions. So one function plus or minus another. And we can write the plus or minus here because the rule is essentially going to look the same for addition as it does for subtraction. The derivative of a sum or difference is the sum or difference of the individual derivatives. So essentially what this is going to look like is the derivative operator distributes to each of the functions. So if we're differentiating a sum or a difference, we can actually take the derivative of the individual functions themselves. So we can take the derivative of f of x, we can take the derivative of g of x, the function that was added or subtracted, and then based on the operation that was combining them, we can just add or subtract those individual derivatives. So this is very formal looking, but if we think about what this really means, what it's really saying is that any function that involves a sum or difference of several terms can be differentiated term by term. That's essentially what it means. So anytime we have more than one term in our expression and we want to differentiate, we can differentiate one term at a time. The derivative of one is independent of the derivative of the other. We can take individual derivatives, and then based on whether they were combined with addition or subtraction, we just combine the derivatives together at the end. So let's look at a couple examples where we have more than one term involved. Okay, so our first function, y is equal to 5x cubed minus 7. So let's break down the structure of this before we look at the derivative. Well, first off, we have two terms, and notice they're combined by subtraction. Now let's focus on the first term. So there's a couple things going on in the first term. We have a constant multiplied by something else, and that something else is going to be a base with a constant power. So we have the constant times a function, and then we also have a situation where the power rule will apply because we have that x cubed. Now for our second term, notice it's just a constant by itself. There's no variable present. So differentiating this by itself would require the constant rule. And now that we have the sum and difference rules, what that tells us is that we can look at each individual derivative one at a time and then just combine those individual derivatives with subtraction. So when we differentiate this, let's see if we can do this without actually writing out all the individual steps. Again, we're just thinking term by term. What is this going to look like? So the derivative of y with respect to x. Now let's focus on the first term. So constant times a function tells me, essentially forget about the 5. The 5 could be pulled out front, we deal with it later. We're focused on that x cubed. So the power rule tells me when I differentiate that x cubed, I'm going to bring down the exponent and then decrease it by 1. But notice when we bring down that exponent, it's going to be multiplied by that 5 that we still have out front. So if we bring down the 3, it's going to be multiplied by our 5 for a coefficient of 15. And then we have our x that started with an exponent of 3. We're going to decrease the exponent by 1, which is going to give us an x squared. Now what about this particular derivative? So we know based on the difference rule that if we're subtracting two terms, we can also just subtract their derivatives. So there's going to be a subtraction involved. What about this individual term treated as an independent function? Well, remember, it's just a constant. When we differentiate just a constant, no variable involved, the derivative is 0. So that means our actual derivative, if we write that a little bit more cleanly, is going to be 15x squared. Okay, let's try one more. Y is equal to 24x minus the square root of x plus 5 over x. So we have 1, 2, 3 terms. We have a difference, and then we have a sum. So the sum and difference rules tell us we can look at these individual 3 terms by themselves, differentiate each individual term, and then just combine those derivatives together with subtraction first, and then addition second. Now the first term, that one's not going to be too bad because it's just going to be a power rule type situation. That x has an implied exponent of 1. So we can use the power rule on that. Now what about the next term? We have a square root. We don't have a square root rule, but remember we have a way of writing this square root as an exponent. So we're going to have to rewrite things in a different way in order to use our rules here. So 24x, that'll be fine. The square root of x, remember there's an implied 2 that's not written, they're in the window. If we want to write this in an exponential form, we're going to keep our base, x, and then the exponent is going to be 1 divided by whatever that index is. So a square root is the same thing as an exponent of 1/2. And then our last term, which is added, remember again, we don't have a rule for division at this point, but anything in the denominator could be written in the numerator with a negative exponent. So negative exponent means take the reciprocal. If we go backwards, this is again an x to the first power, but if we want to write it outside the denominator, we're going to write it with an exponent of -1. So this is going to be the alternative version of our function that's going to allow us to use the rules that we have so far. And again, the sum and difference rules tell us we can look at each individual term one at a time, take the derivative of each of them, and then just add and subtract them from there. So 24x, remember there's an exponent of 1, so we bring down the exponent, that becomes a factor. 1 times 24 is going to be 24. And then we decrease the exponent on x, so 1 minus 1 will be 0. Well, anything to the 0 power is just 1, which means the x is going to go away. So the derivative of 24x is just going to be 24. Now using the difference rule, I know I'm going to be able to just subtract the derivative of the next term. Now this is also a power rule situation, so we know that we bring down the exponent, and then we decrease that exponent by 1. So x raised to the 1/2 minus 1 is going to be -1/2. And if you need, take that, go out to the side, 1/2 minus 1, make sure you can simplify that down to a -1/2. And then our last term, which is added, the sum rule tells us we can just add the derivatives. Power rule, bring down the -1. It's multiplied by that 5 that's already there. So -1 times 5 is going to be -5. And then we decrease the exponent by 1. So -1 is going to become a -2. All we have to do now is just clean this up. We don't want negative exponents. We want to avoid those. And then it looks like we've got a couple issues with the signs right there. We need to clean that up. So 24. Now let's look at this next one. So 1/2 times x to the -1/2. There's a couple things going on here. We need to deal with the negative. We need to deal with the 1/2. Let's just deal with the negative first. So remember, the negative exponent tells us take the reciprocal. In other words, move it to the denominator. So 24 minus 1 over 2x to the 1/2. Okay, and then our last term, a positive and a negative, we can turn that into a subtraction. We have a 5 then, because remember we've taken care of the sign now, times x to the -2. So that negative exponent, again, that means flip it, take it to the denominator. 5 doesn't have a denominator yet, so that's just going to be 5 divided by x squared. Now the only other thing we may want to do is convert this fractional exponent back to a radical. Because it has a numerator of 1, it's not going to be both an exponent and a radical. An exponent of 1/2 is the same thing as a square root. So we can just rewrite this as the square root of x, and that'll look a little bit better. That'll be a little bit more cleaner, a little bit more meaningful. So 1 divided by 2 times the square root of x minus 5 over x squared. That is going to be our derivative. So we actually used all of our rules there, excluding the constant rule, which we used right here. So notice that's a fairly complex function. The idea of trying to evaluate the difference quotient for this function, where you'd have to plug in x plus h, so many different locations, try to simplify that, combine with other terms, that would be very complex to do. So having these derivative rules is going to be very, very helpful. Now, where did these rules come from? Well, technically speaking, they came from the difference quotient and taking the limit of the difference quotient. So mathematicians were able to use the difference quotient essentially the way we use the difference quotient here. So if you can generate what a function looks like in general and show that that function in general has a derivative that behaves a specific way, then essentially you develop a rule for evaluating derivatives of those particular types of functions with those particular structures. So all of these rules that we've looked at do in fact come from the difference quotient, but evaluating them using the difference quotient is just a little bit more complex than we're really ready for. So we're going to use these rules, and as you can see, they're going to be pretty major time savers. So let's take it one step further. So recall that the derivative represents instantaneous change. It's the instantaneous rate of change. In other words, the change at a single point at a particular value of x. Or alternatively, we can think of it as the slope of the tangent line at that value of x. And so when we looked at derivatives defined using the difference quotient, we found the derivatives, we found them at a particular value of x, and then we were also able to generate the equation of the tangent line at that particular location based on the fact that we have a point and we know the slope from that derivative. So let's repeat that kind of process, but let's repeat it now that we have these derivative rules, these time savers, these great things to use to calculate derivatives. So we want to find an equation in slope-intercept form. Remember, that means y is equal to mx plus b, sort of our preferred linear form. We want to find an equation of the tangent line to the graph of this particular function at each of the following points, and we have 3 different points. Okay, so there's a few layers to doing a problem like this. Now, anytime we see the term tangent line, remember the tangent line has a slope defined by the derivative. Now, anytime we want to find the equation of a line, we need a slope, we need a point. Well, we've been given the points for each of these individual lines we want to find, but we need to have the slope. Since we're talking about a tangent line, the slope is defined as the derivative, or the value of the derivative at each of these 3 locations. So the first thing we're going to want to do is find the derivative for our function so that we can find the slope of that tangent line, which again is going to be important for writing the equation. So because we have our function written in function notation, let's just use the prime notation for the derivative. Now our function here has 3 terms. We have a difference, we have a sum. Remember that sum difference rule tells us we can just look at each individual term one at a time, take the derivative of each term one at a time. So for our first term, we have x cubed, so power rule. Bring down the exponent and then decrease the exponent by 1. So 3 times x squared. Then we are subtracting the derivative of the next term. So x has an exponent of 1. So we bring down the exponent. We can multiply it by the constant that's already there. Remember, constant times derivative says the constant out front doesn't affect the derivative. So we can multiply the 1 times the 2 that's already there for a coefficient of 2. and then we decrease our exponent by 1. So 1 minus 1 is 0. Anything to the 0 power is just 1, so the x goes away, and we're just left with that 2. And then we're adding on the derivative of this last term. This last term is a constant. When we take the derivative of a constant, the result is 0. So technically there's a plus 0 added on if we wanted to be really, really specific. So this is going to be the derivative. So think of this as the formula for slope of the tangent line. That is what this represents. If we're talking about this particular function, f of x, and we want to find the equation of the tangent line to specific points on the graph, this is going to be the formula that helps us find the slope of each of those lines. So at each of these individual points, this is going to be the formula we use to calculate the specific value of m. So for the point 2, 5, f prime of x means we have to evaluate f prime of 2 since we think of x as our input. So our slope in this case is going to be f prime of 2, and then we just plug that 2 into our formula for the derivative. So 3 times 2 squared minus 2. Okay, so 2 squared is 4. 4 times 3 is 12. 12 minus 2 is 10. So that's going to be a slope of 10. Now anytime we want to find the equation of a line, a good option is the point slope formula, which uses a point and a slope. So y minus y1 is equal to m times x minus x1. We can use this formula now because we have our point. This is our x1, this is our y1, and we have our slope, which is 10. So at this point, it's just a substitution. Now remember the x and y with these subscripts, that's where we're going to substitute in our x and y. The x and y without subscripts, those are our independent and dependent variables that form our actual equation. So y minus y1, which is 5, is equal to m, which is 10, times x minus x1, which is 2. And we want slope-intercept form, which essentially means take this and clean it up and isolate y. So y minus 5 is equal to 10x minus 20. And then if we add our 5, move it over, combine with the negative 20, be very careful with your signs. Y is equal to 10x, and then negative 20 plus 5 is going to be negative 15. So if we were to sketch this graph, locate the point 2, 5, and then draw the tangent line at that location, which will be unique. It will be a unique line. This would be the equation of that line. Okay, let's try the next one. At the point negative 1, 2, find the equation of the tangent line. So again, just as before, we need a slope and we need a point in order to use the point slope formula. Well, we have the point, we need the slope. Since it's a tangent line, the slope is given by the derivative evaluated at this particular value of x. So our slope in this case is going to be f prime of negative 1. So that's going to be 3 times negative 1 squared minus 2. Okay, negative 1 squared is 1. 1 times 3 is 3. 3 minus 2 is 1. So at this particular location, the tangent line would have a slope of positive 1. So subbing in to our point slope formula, and it's a good idea to write down a formula each time you use it. That way it's just direct substitution. So y minus y1 is going to be y minus 2 is equal to our slope, which is m, which is 1, times x minus x1, which is x minus negative 1. So watch your signs here, the double negatives, of course that turns into an addition. Now we're multiplying by 1. Distributing a 1 won't really do anything. So we can essentially just drop this off because it's then understood. So y minus 2 is equal to x plus 1. And because we want slope-intercept form, we need to isolate our y. Add the 2, combine your like terms. So y is equal to x plus 3. Now notice we have a totally different line, different slope, different y-intercept. That's because we're talking about a different location on this graph. We're talking about the tangent line at each of these locations. So because these are at very different locations, the graph looks different at each of these locations. So the tangent line will also look very different at each of these locations. Okay, last one. Find the tangent line at the point 1, 0. So again, we need our slope. So in this case, f prime of this x value, which is 0. So that's going to be 3 times 0 squared minus 2. Well, the first term evaluates to 0, and we're left with a negative 2. So in this case, our slope is going to be negative 2. So using point slope, y minus y1 is equal to m times x minus x1. And now we can sub in our values here. So y minus y1, y minus 1 is equal to our slope, which is negative 2, times x minus x1, which is x minus 0 in this case. Okay, clean it up. Now distributing the negative 2 here, this 0, this goes away. So that's just going to be negative 2x. So y minus 1 is equal to negative 2x. And then in slope-intercept form, move your 1 over, y is equal to negative 2x plus 1. So notice in this case, the slope is now negative, which means if we think graphically speaking, both of these slopes are positive, which means if we were to look at the graph is sloped upward, so we would draw a tangent line that has a positive slope. In this case, at 0, 1, because the tangent line has a negative slope, that means the graph is sloped downward, and if we were to draw the tangent line, it would be a line that has a negative slope. Now, if we go from having a negative slope to having a positive slope, what that really means is that somewhere in the middle, we turned around and changed directions on our graph. And that's actually what we're going to talk about in the next chapter, is how we can use the derivative to determine some things about a function like this. So we know how to find intercepts for a function, but getting more detail other than that really just requires plotting points until we have enough points to draw a graph. Well, one of the key locations on any polynomial graph is going to be a location where the graph turns, what we call a turning point. Those will be locations where we see specific behavior with the tangent line, where we go from a positive slope to a negative slope, or vice versa. So using the derivative to analyze what we see with a function, we're going to see changes like this, where the slope of that tangent line changes. Of course, we'll get there. We're not there yet, but that's just sort of a preview of the kind of things we'll be doing, the kind of ways we'll be using the derivative. Let's look at one final example. Let's look at an application where we can calculate a derivative in a real situation. So the temperature defined by T of a person during an illness is given by the following function. So T of T, now be careful, make sure you differentiate between the two. Capital T is the name of our function, lowercase t is our input, our independent variable. So T, capital T, is temperature in degrees Fahrenheit, and lowercase t is the time elapsed in days. So we think of time as being our input, and then based on the time we input, we get a value out that represents temperature in degrees Fahrenheit. So we want to find each of the following. The first thing we want to find is the rate of change of the temperature with respect to time. Now notice here that we don't have anything involving an actual number. We're just looking for the general rate of change of temperature with respect to time. And it's implied here that we're looking for the instantaneous rate of change with respect to temperature. So that, by definition, is the derivative. It's the derivative of temperature with respect to time. Or alternatively, we could write this as T prime of T. Remember, the derivative is defined as our instantaneous rate of change at a single point, in this case, a single point of time. But here, because we don't have any specific constant numbers involved, what we're looking for is this general derivative, the formula for finding the actual value at any specific value of lowercase t. So we need to differentiate this function. Now don't be alarmed by all the decimal numbers. The rules apply in the same way as they did before, and you have your calculator. If you need your calculator, you use your calculator. So t prime of t, or the derivative of t with respect to time. Now we have 3 terms. The sum rule tells us we can go one term at a time, take the individual derivatives one term at a time. So let's look at that first term. We have a constant coefficient, and then we have an exponent. So we can use the constant times a function rule, and we can use the power rule. So we're going to bring down our exponent, multiply it by that pre-existing constant, and if you need, it's okay, you can use your calculator. So negative 0.1 times 2, when we bring that exponent down, that's going to be our new coefficient. So negative 0.2, and then we decrease the exponent by 1. So t squared becomes t to the first power, and of course we don't write the 1. Now for our next term, 1.2t, remember there's an implied exponent of 1. We bring down our exponent, multiply it by that pre-existing coefficient, which is 1.2, so 1 times 1.2 is 1.2. Decrease your exponent by 1, which means the t goes away, so that's going to be the derivative for that term. And then our last term, 98.6, that looks familiar. That's your standard body temperature, right? 98.6 is a constant in this case. There's no variable attached to this term. So when we differentiate this constant, its derivative is 0, which means this is going to be our fully simplified derivative. We can't combine our like terms, so that's going to be the formula for our rate of change of temperature, capital T, with respect to time in days, lowercase t. The next thing we want to find is the temperature at t equals 1.5 days. Now be careful here. Pay attention to actually what it's asking for. It's asking for the temperature. And let's preview the next thing that we're going to look for. The next thing we're looking for is the rate of change of temperature at t equals 1.5 days. We're not looking for the same thing in these two parts. Here we want the actual temperature. Here we want to know how quickly the temperature is changing, either increasing or decreasing. So if we're looking for the actual value of the temperature, we're going to get that from the original function. The original function represents temperature at a specific time, represented by lowercase t. The derivative represents the rate of change of temperature. So the key words here, either there or not there, are rate of change. Here we don't see anything mentioned about rate of change, so we're just looking for the actual temperature itself, specifically when t is 1.5. So we're evaluating the function t at an input value of 1.5. So that's going to be negative 0.1 times 1.5 quantity squared plus 1.2 times 1.5 plus 98.6. So let's evaluate this in the calculator. So negative 0.1 times 1.5 squared plus 1.2 times 1.5 plus 98.6. And of course, double check that you typed what you intended to type. Okay, that looks good. And so there we go. Notice it doesn't say anything about rounding, so do not round. So that's going to be 100.175. Well, 100.175 what? What is our unit? We're talking about temperature. We're inputting a number of days, and it says that the output is temperature in degrees Fahrenheit. So because it's an applied problem, we do want to write the units so that we know what we're talking about here. So that's going to be degrees Fahrenheit. So after 1.5 days, this particular person, modeled by this function, has a temperature of 100.175 degrees Fahrenheit. Now, last but not least, what is the rate of change of the temperature at 1.5 days? In other words, at the moment when this is the temperature, how quickly is the temperature changing? And more than likely it's going to continue going up, right? Because we've started at 98.6, We have a higher temperature now. What we want to know is at that single moment when we've hit 1.5 days, and this is the temperature, at that single moment, how quickly is the temperature changing? So we want to evaluate the derivative with an input of 1.5 days. So that's going to be negative 0.2 times 1.5 plus 1.2. And again, we can do this in the calculator. So negative 0.2 times 1.5 plus 1.2. And that's going to give us 0.9. Now again, what is our unit here? Here we're going to have to be a little bit more careful because we're talking about a rate. Rate involves two different units. It's hard to see the rate using this notation, but if we focus on the Leibniz notation, dt, derivative of temperature with respect to time, that'll help us determine what the rate is going to be. If we think of the units for the numerator and the units for the denominator, that's going to give us a way to write our actual unit involving our rate of change. So the unit for temperature is going to be degrees Fahrenheit, and the unit for time is going to be days. So if we write the ratio of those two units, that's going to give us the unit for our rate of change. So that's going to be degrees Fahrenheit per day. In other words, at this specific temperature, at 1.5 days, this is how quickly temperature is changing. So it's changing 0.9 degrees Fahrenheit per day. That is the rate of change at that exact moment under these specific conditions. So that gives you an example of how you might use the derivative in a specific situation. Derivative represents instantaneous change. Now if we're talking about average change, maybe changing over the course of one day, so going from maybe the first day to the second day, something like that, we're talking about average rate of change. Here we're talking about the instantaneous rate of change, how we're changing at that single point in time at that single temperature. So just to review, we looked at a few derivative rules here. So we've introduced the constant rule, which is going to allow us to differentiate a function that's just a constant, no variable. We talked about the power rule, which will allow us to differentiate something that involves a variable base raised to a constant power. It is going to be important that the power is a constant number, not a variable. We also talked about the constant times the derivative rule, which essentially says if you've got a coefficient on your function, don't worry about that, just factor it into the derivative after you differentiate the rest of the function. And then we also talked about the sum and difference rules, which are going to allow us to differentiate term by term. So in a function like this that has more than one term, 3 terms added together, we can take the derivative of each individual term one at a time. So this still restricts us to fairly simple functions. In the next video, we're going to add on a couple of additional rules that will allow us to take derivatives of slightly more complicated functions.